Yeah, now it's coming. My input is a pulse. My output is also a pulse. So suppose you want, you can remove this grid lines. That is grid off. So you can make it into stack mode. So here you can see the waveform, right? So your input is a pulse waveform and the output is also the inverted pulse waveform of your input. So here you can see, suppose you want the power value and the result value. Here you can see the power value. So this is the average power it's consuming. I have done some mistake. I think I'll rectify this delay. Again, I'll show this. Okay. So this power value is showing here. Suppose if you want the DC analysis, we can do the DC analysis also. Make the DC analysis. Doing both AC and DC analysis. For DC analysis purpose, I am applying my input as a DC source. So my input is as a DC source. The DC value I am changing from 0 to 9 with the value of step value 0.1 and the corresponding DC value what is coming. Let me check. Yeah. So here you can see. Here we have kept the paper, the list open, DC, your input, and your corresponding output. So down, you can see, right? So input is varied linearly with the step value of 0.1. The corresponding output, inverted output. This is the voltage transfer characteristics of your inverter. You would have seen in your theory works. Yeah, if you have any doubt, you can ask your doubt. Otherwise, or you want, if you have any circuit, you can suggest the circuit. For the circuit, how to make the code, I'll explain you. People, anybody, you are interested for doing the research on CNTFET? If you have any doubt, you can ask it. For NAND gate, yeah. Can you do for comparator? Vrindamam, comparator, no. You have the CMOS code for comparator, definitely I'll do it. You have the comparator CMOS circuit. Please give the circuit, I can write the code for that. Okay, suppose for simple gate, I'm saying for NAND gate, one of the participants, Venkata Lakshmi asked NAND gate, let me write the code for NAND gate and I'll try to implement here. Okay. It is not difficult for the big circuit, but it takes more time. That's it, nothing else. Any of you implemented your means you have installed your HSPICE. You can meanwhile do this operation. If you are finding any error or any question, you can ask. Yeah, here I want to emphasize one thing. See, suppose my inputs are A and B, my output is Z. For the same case, I write the code. Yeah, first I'm writing the X. I'm saying X1 is my Q, transistor 1, N MOSFET 1. Drain is connected with Z. So Z. Gate is connected with A. Its source is connected with the drain of another transistor, right? Source is connected with the drain of. Is it visible? Is it visible? Shall I have to zoom it? Is it visible? Yes, thank you. Yeah. So when two terminals connected like this, for that what you have to use, you can use any letter symbol which is not you are using in your circuit. Suppose I'm using this portion. Suppose now I'm saying this input A, I'm taking B in 1 or input 1. Input 1 I'm saying. This is my input 1. B in 1 I'm saying. B take input 2. So is that I'm taking V out. V out. V in. This junction I'm saying A. Anyhow, the source substrate of NMOS is connected with ground. Next, similarly, for the second gate I'm writing this B I'm saying input 2. So X2, it is V out. Sorry, not is it is V out. Drain is A. A. Here I'm saying A, and V in 2. This portion is my B. I'm saying V in 2, and then source is ground. Substrate is also ground. For third transistor, suppose I'm saying this transistor, P MOSFET. I'm saying X3. So X3 out, V out, and X3 V out. Input is connected with the V in 1, and its drain is connected with source is connected with the VDD. Substrate is also connected with VDD. For the fourth transistor, I'm saying this is VDD. Fourth transistor I'm writing. Suppose it is X4. Again, it is out, V into VDD. So V out, V into VDD. Please raise your question if you have. Otherwise, I'll proceed. This is how to write the code for or write the netlist for your digital circuit in your here in your HSPICE. So same code. Suppose I'm taking the same test I'm doing here. I'm going to apply the first one based on this circuit. So I take this code there and I'll correct my code here. I keep this code here for my reference. Based on this, I'll do my correction. So output is our first gate. These two are mine. I know well. These two are mine. N MOSFET. Is there any specific order for listening? One of the audience, they are asking the question. Let me check. Is there any specific order for listing the inputs and outputs? Like, are you about input ordering, ma'am? Low power technology, madam. You can unmute. You can speak. Are you asking about input ordering? It is one of the technology for low power technology, low power, right? Are you asking about that? Like Verilog? Yes, sir. No, ma'am. Actually, I I never bother about that. If you are interested, you search about that. Okay. You can write. I think your question is, instead of representing this transistor first, if I represent this transistor first, what is happening? That is the question, I think. This input ordering, I never search, I never tried. If you are interested, you try. Otherwise, I try. Let me check. We'll check now. Here itself we will check. Fine. Shall I proceed? So first one is V out, and V in one, V in one. Here I am saying it is A ground. Second transistor is also N MOSFET. I am taking the N MOSFET port. Netlist. So this is my second transistor 2. So here it is A, B into ground. Third transistor, it is P MOSFET. Let me unmute this.
Some very that makes
Shanam, are you raising the question or you are speaking with your colleague or anybody else? It is disturbing our class. So X3 it is V out and then V in 1, VDD. Next X3. Next X4. That is also P MOSFET. So X4, it is V out, V in 2, VDD. So here we have two inputs. Just a minute, I'll mute Vishnu, then I'll.
right answer is okay.
Yeah, so this is the code. We have two inputs. I'm deleting this portion. What is mean by cube is equal to 3? Thank you. What it means already I shown here, right? But here, how many parallel CNTs we are using? That is T tube is equal to 3. How many carbon nanotubes you are using as a channel? How many parallel tubes we are using? Is it okay, ma'am? Ma'am, is it okay? Yeah. So here we have two inputs. So I'm changing my input.
Okay.
We have two inputs. My first input and second input. I'm taking first input as a V in 1, and the second input is suppose voltage source 2. I'm saying here I am. Someone is asking question. Let me complete this portion. I will come and answer. V in 2. Suppose I am changing the period of V in 2. It is instead of I am taking suppose 25 I am taking for a condition for knowing all the conditions 25 nanoseconds on time out of 50, even 100, your wish. Someone is asking the question. Let me check the question. What is it? What is the syntax for writing x1, x2? That is representing your T. Is it the question like why we are using X1, X2, X3? For representing CNTFET, we are using this. Suppose in case of your MOSFET, we can use M1, M1, M2, M3, M4. Shall I proceed? So again, here also I'm doing. Yeah. Here again I'm doing. I'm doing my transient analysis. So I mute my DC. So I must save my code. Let me check whether my code is correct or not. Yeah. So I'm doing the analysis. I saved my code. Yes. Now I'm running. Test open analysis. I think I am not representing these values. Sorry, here V in one. It is your what are the things you want to plot or waveform? What are the waveforms you want to see that you have to represent by V plot? So V in one, V in two, V in one, V in two, V out. Okay. Sorry, I forgot to represent these things. So again, I'm running in simulation. Open, test, open, incident. So input one, input two, output. So let me check. Grid off. So NAND gate, stack mode. NAND gate. When both the inputs are zero, or at least one input is zero, output is one, right? Both the inputs are one, output is zero. Here, this input is 1, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0. It is correct, right? This line is here, both values are, no, both values are merging. That's why this line is coming. Please ask your doubt if you have. Suppose for your kind, for the thing, we'll check this power value. Okay. Suppose for this case, what is the power value is coming? Tube value I kept 1, right? So what is the power value I am getting? So 1.30 into 1.30 nanowatts. Fine. 1.3045 nanowatts. Suppose if I increase number of tubes, the power consumption will be increased. Why? Because of increasing number of tubes, it will be increasing number of electrons in the channel. So suppose instead of I'm increasing, I'm doubling this value. I'm increasing this value. Some glitches. That's what I'm saying now. That glitches it is due to the lines are merging, that rising transients. I'm not changing the logic, just number of tubes I'm varying. Let's check what is the power it is coming. Yeah. So already we had 1.3 nano, here 2.54 nano. So the power is increasing. Can you observe? The power is increasing. Even I can increase the temperature value. See, suppose Smita Shetty, ma'am, are you asking doubt or you are unknowingly you unmuted your mic? Suppose I'm increasing temperature value 50 I'm keeping. So now the tube value is 6 and we got the value of 2.5, right? 2.5 nanowatts. Just I'm increasing my temperature. Let me check what is happening. So just I'm seeing the power value. See, it comes 3 nanowatts. So as increasing the temperature, the power value is increasing. It's okay, ma'am. Any other doubt you can ask. If you have any doubt, please ask your doubt. What are the possibilities? If you are, so suppose ma'am, Venkatalakshmi ma'am asked, right? Changing the input ordering. Let me change it. Suppose I'm changing. So finally we got the power value like, let me check the power value, just I'm changing the order, pin ordering. So 3 nanowatts, right now we have 3.012 nanowatts. So I'm changing the order. So X3 I'm keeping here and X4 I'm keeping here. Is this right? Is this right? So I changed the pin order. The pin order in the sense, as per the circuit, already we represented this circuit first and then this fellow. Now we are changing. First we are representing this and this. No, yeah. V1 is here. V1 is with Q3. V2 is with Q4. Suppose if I am changing, V2 is instead of changing here, I think I can change here. Am I audible? Am I audible? Am I audible? Yes. My screen is visible, right? Shall I proceed? Yes, thank you. Suppose
So parameter,
already what we have.
this one.
Yes, ma'am.
This parameter x3 v out, for example, x3 v out v in, and after that we have LCH LG, these lines.
Yeah.
What are those?
What is this parameter you are asking?
Why we should mention in a particular value is there, or randomly we can take those values?
This value, ma'am, exactly, it is gate length, all the values. Gate length, effective gate length.
Where do we get, sir, those values? How to know
these
that?
things, it is there in your model file.
Okay.
Okay. If you are interested, you go. That's what I'm asking. You download Stanford University model file. You go through all the parameters. Is it okay, ma'am? Hello. Shall I proceed? Shall I proceed? Yes. Input ordering. Suppose I'm guessing, is it right? Instead of keeping here V1, shall I keep V2 here and V1 here? That is also changing the input ordering, right? So wherever V1 is present, there I am making as V2. This I am saying V2. This V1. This is V1 and this is V2. Is it right? So just I'm saving this result. I'm simulating this value. So I'm checking my functionality. V in packed mode. So again, it is meet out the functionality. So let me check the power. Already we had 3 nanowatts. Now a little bit change, right? Already. Can you see? Yeah. So a little bit of variation. Or it's decreasing. Any other queries, you can ask your question. If you have any question, please ask your question. One of the paper, they reported like instead of using common chiral vector for all the CNTs, how they have used for all the P MOSFET, they have used 16,0. For all the N MOSFET, they have used 19,0. That is also one of the research. Suppose for this case also I am doing. Right now, what is the power? Nothing I'm changing. I'm going to change the chiral vector. Right now, I'm getting the power value of 2.89 nanowatts. So just keep in mind it's 2.89 nanowatts. So I'm changing my P MOSFET chiral vector as M is equal to 16. M is equal to 16. N equal to 0. For N MOSFET, it is 19 only. So I'm using this chiral value. How it is varying the power? Let me check. Sir, you mentioned about delay. Have you changed it? So time delay is just. Vrindavan, just a minute, I'm coming. I'll come to your question. Yeah, listen, power is well decreased, right? Instead of rather than using common serial vector for all the devices, if you are using different serial vector like a PCNTFET with a serial vector of 16,0, all NCNTFET with the value of 19,0, the power is well decreased. Sorry, it is minimized. Already we had a 2.89 something. Now we have 2.13 something. Vrindavan, sir, you mentioned about delay. Have you changed it? So to find delay is the syntax. Delay is the syntax, mom. This is the syntax we have to use. Dot measure. This power is average power is a syntax. Similarly, there's dot tran delay. Delay between input to output. Actually, here we are not using here, right? Suppose V in 1 2, V in 1 2, V out. Let me check delay is coming or not. Yes, sir. So from input 1 to output, what is the delay it's coming? Let me simulate this. Let me check. So I want to check the delay whether it's coming or not. Yeah, delay it's coming. Negative value it's coming. Anyhow, it's not negative value. It is 2.49. Or otherwise, let me check delay between input 2 to output what it's coming. Input 2 to V out what it's coming.
It's 5,000. We have taken every step in ensuring.
Yeah, this is the delay it's coming. 3.578 picoseconds. So these are the syntax. This is the syntax for power and this is the syntax for delay. Any more question? You can ask your question.
Excuse me, sir.
Yes, ma'am.
Sir, you have interchanged the input ordering V in 1 and 2, and you have shown very well that the power has reduced. Is there any logic to check when the power will be getting reduced, sir?
You are asking pin ordering. You are asking.
Yes, sir. Yes, sir.
Ma'am, I never tried pin ordering, ma'am. I think pin ordering means I never tried. Okay. I can say actually when this pin ordering is effective, we have to keep the low threshold voltage circuit near to the VDD, low threshold voltage device near to the VDD, and a high threshold voltage away from the VDD. Like that, I have studied.
Oh.
That is the only logic I know.
Okay, sir.
Any other question? Anybody interested to do this, their work on CNTFET, you can contact me. A little bit I know means how to make a digital circuit using CNTFET, even analog circuit also. Okay, so how to make use of it in HSPICE, I know a little bit. If you are interested or you are interested to do your research work on this, I'm ready to help for you. You have any more queries? Please ask your queries regarding this Netlist or HSPICE or in general CNTFET.
Sir, good afternoon, sir.
Yes, sir.
Sir, what about area, sir?
Sir, no, actually, for the CNTFET, making this CNTFET, no, generally we need a, no, we have to make the layout, right? If you are interested, you can make this CNTFET in Cadence. You can invoke the CNTFET in Cadence. There we can find the area, sir.
Okay.
Okay, this HSPICE is not supporting for a area. Hello, sir.
Thank you, sir.
Yeah, thank you, sir.
Hello, sir.
Yes, ma'am.
Sir, we have listed four things, X1, X2, X3, X4. How will the software identify which one is the NMOS and which one is the PMOS FET?
That we have to represent here, ma'am.
Okay, sir.
That's why whenever you are copying for a PMOS, mostly I use this netlist only. Whenever you are taking for PMOS, take from PMOS and do the changes there.
Okay, sir.
Yeah.
And then while listing at V out, V in one, VDD, is there any order for that, sir? First, we have to mention the
That's what I'm
terminals.
saying. That's what I'm saying. First of all, we have to say the device name, X1, X2 like that.
Okay, sir.
Next one is drain.
Okay, sir. And this is what I'm
First
asking.
terminal is drain, ma'am.
Okay.
First terminal is drain. Second terminal is gate.
Okay.
Next is source.
Okay, sir.
Next
Fine.
is substrate.
Okay, sir.
For all your HSPICE tool, this is the order, ma'am.
Okay, sir. Thank you, sir.
Yeah. Yeah, thank you, ma'am. Any other question? For N MOSFET also same. Are you asking about NG spice? In NG spice. Sir, are you asking NG spice? Mahila Nas. I am not aware of NG spice. Let me check and check. I use H spice only. Ashwati, I'm asking, sir, this is Verilog A code. Are you saying, ma'am, it is a Verilog A code or it is your doubt about it is Verilog A code? It is a yeah, it is Verilog A code only. Because no, while we are invoking this is in your CNTFET, will save as a Verilog A code only. Suppose if you are interested, best thing I'll share the video. I have the video. We can invoke, we can make the symbol of the CNTFET in your Cadence, but you should have the licensed version of Cadence. I'll share that video, that YouTube video. It is 30 minutes video. By using that, we can invoke our CNTFET in Cadence. We can easily do all our work rather than using this HSPICE. Suppose you are not having the facility of Cadence, we can use HSPICE itself. Definitely, ma'am. I'll share it. Any more queries? Ashwati, ma'am, do you have a Cadence by a license version in your college or in your institution? Yes, it's okay, ma'am. Yeah, I'll share. Definitely, I'll share. How to change the technology file? Where, ma'am? How to change the technology file? Where you are asking in Cadence or here, CNTFET? Akadalishmi, ma'am. Code here. Yeah, here we have .lib. Or you are asking about technology file in the sense model file you are asking, right? Library file you are asking. Model file, library file you are asking, right? Yes. So here we have this .lib. This is by using this, but that already I said we can use only for 32 nanometer technology. In Stanford University model only we can use it. That we can include here. By using this command, you can include here. Now is it okay, ma'am? Or you are asking something else? Share HSPICE related documents to with every. Oh, sure. I'll share it in our mail. Okay, definitely I'll share it. Here, my request is, dear participants, please make your attendance. Why I am more often I am insisting this example of analog circuits. Example of analog circuit, but I don't have here. You can try for biomedical amplifiers or sensors, temperature sensor, pressure sensor. That and all you can try. Biomedical amplifier, that would be a best example for your analog circuit. You can make use of in a HSPICE. Up to this session, please make your attendance, because no, after the end of entering all the attendance in the AICT website, I can't make any changes. That's why I'm asking you. If you are attending the session, if you are not putting your attendance, no, by using that sheet only, I am making the attendance. Okay. If you are not mentioning, by mistake, if I am not entering, you will lose your certificate. After that, I also can't do anything. That's why I'm asking you. Please do your attendance. Any more question? Please ask your question here. Any other question regarding this HSPICE or this CNTFET? There is no more question. Can we wind up the session? Can we wind up the session? I think I'm audible. Yeah, thank you so much. Thank you so much. Had a nice time with you. I don't know how much this is useful for you. Thank you so much. Thank you.